Okay, we talked about all the formulas. We didn't do the surface area formulas for these ones, but you should be able to do it part by part. So if I was doing this triangle here, it would be length times the slant height divided by 2, and then there'd be 1, 2, 3, 4 of them. So surface area is equal to length times slant height divided by 2 times 4, and then plus the bottom, which is just length times length. Hopefully you guys can figure things out like that. Same thing with this one. Actually, this one has kind of a funny formula. I don't know if we're actually going to use this formula, and if we were going to, I would definitely give it to you. It's pi r squared plus pi rs. Pi r squared is the bottom, and then pi times r times the slant height ends up being that whole circular part. I don't know if you ever learned that one. And for spheres, I would definitely give you these formulas if we were going to use them. It's 4 pi r squared, which is kind of interesting. That one's just a memorization one as well. Okay, so let's talk about different scale models, and we kind of talked about this on the board last week. In a linear model, if you want to compare one dimension to another dimension and find the scale factor, you would take the image and divide it by the real life one, or the other way around. Basically, you divide two corresponding sides. Now, that's actually a really important word, though. Corresponding. Corresponding means they represent the same side in the image. They can't be different measurements that you're comparing to each other. You need to find the same measurement in both images. And then just take the ratio of them. So k is just equal to the ratio of 1 versus 2. And depending on the context, different ones you want to be on top or on the bottom. Usually the image is on top and real life is on the bottom, but sometimes that's not true. In area, we realized that it was the k value you had to square to determine it. But if you wanted to go backwards and find the k value, you would take 1 over 2, 1's area versus 2's area. So you could take the ratio of the areas and then you could square root them. That would find you the k value. Because k is always in terms of the linear one. How much is one length growing by? So the area, the ratio of the areas need to be square rooted to find what that amount of growth is. What do you think it is going to be for volume? Maybe I'm jumping here. That's for surface area. What is it for volume? Well, if you had the first one's volume, you would divide it by the second one's volume, and then you would cube root it. So it is actually the factor cubed if the units are cubed. And that should be somewhat intuitive. In order to find cube rooting on your calculator, everyone's a bit different. I'll show you mine. So I've got squaring, I've got square rooting. Up here I have the xth root. So I would do it that way. And I think you put the 3 in first. I would do it 3 shift xth root of, I don't know, let's say the ratio is 16. And then I would find the factor is 2.5 times bigger each side length. Something like that. Or you can do it to the power of, I actually usually do this. I would do 16 to the power of, and roots are fractions. So that's actually 1 over 3 is the third root. And that should give you the same number as well. So either of those, sometimes it looks like y to the x, or it's going to be xth root, something like that. Hopefully you can find that. Maybe you should try it yourself. Try and find the third root of 16. See if you can get 2.51. So pause it here. Oh, I forgot to say you don't have this part. This is just for summary. So if the units are linear, then the k value is just equal to the images divided by each other. If you're doing it with units squared, you can find the k value by doing the different images divided by each other and then square rooting them. And if the image if the units are cubed, you would take your two images and then you would cube root the ratio of them to find your k value. Just something like that. So let's put it in action. Or the other way you could say it is you would take 1 and you would times it by your k value cubed to get to 2. That's the other way to write it. So if you have the k value and you want to find the new image, you times it by the k value cubed to get to your new one. If you have both images and trying to find the k value, you can actually rearrange this. So you divide by 1, and then you cube root. So 2 over 1 cube root, or 1 over 2 cube root. Either way works just fine. Okay, a cylinder has a surface area of 48 centimeters squared. If the cylinder is doubled in size, what will be the new surface area? So we're going to take 48, and we're going to times it by 2, and these are squared units. So times 2 squared. That should be the new surface area. 48 times 2 squared is 192 units, centimeters squared. Easy. So therefore, blah, blah, blah. A large, do you guys have this one? Yeah. An extra large Kleenex box has a volume of 3,600 centimeters cubed. A smaller box, which is similar in shape, they don't say similar. This only works if they're similar shapes, if they have the exact same shape, just different sizes. That's the only time you can apply this. A smaller box has a volume of 56.25. What's the scale factor? So I would probably put the small one on top, so we can say it's 1 to something, small to big. So I would say it's 56.25 divided by the large one, 3,600. Now these are cubic units, so we need to cube root it. And try and find what that is. I get 0.25. Try and use all your decimal places until the very end, so you don't end up rounding. Which means the smaller image is 0.25 times the larger image, or you could do this as a ratio. It's 1 to 4. What is the scale factor relating the smaller to the larger box? The smaller, so therefore, smaller to larger box has a scale factor of 1 to 4. And you can turn this back into a fraction. Really good calculators nowadays have a thing that turns that right into a fraction, but this one you can kind of see is going to be 1 over 4. So it's 1 to 4. Good? Good. You don't want to do 4 to 1 in this one because it tells you the order. It tells you I want smaller compared to larger. So smaller compared to larger. So if it gives you the order, be careful of the order. Otherwise, you'd tell me 4 to 1. And I know you did all the right math, but you didn't understand the question correctly. So it'd have to be a half mark off. Okay. About how much more air is inside this basketball compared to a tennis ball? Are they similar in shape? Yeah, every sphere is similar. Well, or at least close enough to being similar. We know the radius is 4.7, radius is 3.3. So first thing we want to do is find the scale factor. Let's say big compared to small, so 4.7 compared to 3.3. Is 1.42 line repeated, 424242. And keep that number in your calculator, because we want to use that number with all its decimal places. So don't just clear your calculator and use 1.42. So now how much more air will be inside the big ball? It doesn't tell you how much air is inside, how much more air is inside the basketball compared to the tennis ball. Yeah, it doesn't tell you how much air is inside either of them. So we need to only talk about how much more it is. And the best way to do that is treat the small volume like it's 1. If it was 1, then whatever the new ball is just tells you how much bigger it is. If the new ball was 3, then the volume is 3 times bigger. If the new ball is 5.7, then the basketball is 5.7 times bigger. So if the volume was 1, what do we say? It's going to be the original volume times our K value cubed, because it's cubic units. So we want to cube that. It's going to amplify 3 times as it grows. So the new volume is going to be please make sure you used enough decimal places. Let's round it to 2 though at this point. So it should be 2.89 roughly. Use a little dot to say roughly, and units, centimeters cubed. Actually, it's not units. Sorry, scratch that. Because we're not saying it actually contains 2.89. We're saying it's 2.89 times bigger. Because this wasn't an actual unit. This was just a rate or something. It's a little bit tricky. So therefore, the basketball contains 2.89 times more volume than the tennis ball. Good. Hopefully that one's not too confusing. It's weird when you don't have actual numbers to work with. You don't know what the volume of the tennis ball was, but you should be able to do questions like this. There definitely could be ones like that on the test. Example 4. Last one now. I think this is the last one. Yeah. The Great Pyramid of Giza in Egypt, I think this is the biggest pyramid, was built on a square base with the dimensions shown, 230.4 each way. So this is going back to grade 10. This is the side length. We might call that length. This is the slant height, which we call S. And this is the actual height, which we call H. And we need all 3 of those things depending on whether we're doing surface area or volume. An artist who works with plate glass wants to build a replica of the pyramid for an installation at an art gallery. The artist is restricted by the floor dimensions, which are 6 by 6, and the ceiling height of 3.5. As well, the glass sculpture must have room for a 1-meter walkway around its base. Interesting. So I assume that's 1 meter less around its base than the whole 6 by 6. What scale factor might the artist use to build the sculpture? Okay, this is a hard question. I don't know if you're feeling confident, you should pause this and give it a try. If not, you should at least pause it and think about what you would do first, because this is going to be a challenging question. Okay, I'm going to start talking again. So we actually have a pair of restrictions, and we're not sure which is more restrictive. We're not going to make it perfectly fit the height, and we're not going to make it perfectly fit the floor dimension. One of those is going to be our restrictive value, and we're not sure which yet. So we need to do each one individually. So let's do the floor first, because you probably would start with the floor, if I had to guess. So we have an area that's 6 by 6, but we need a 1 meter walkway around this thing. So we need the base of the pyramid to fit inside that little area. And the question is, how big is that area? And this is a tricky question at first until you've seen a couple questions like this. This is 1 meter right here, and this also is 1 meter right here. So the length of this is actually 4. Same thing with the vertical way, that's subtract 1 and then subtract another 1. So it's actually a 4 by 4 area. Okay, now the question is, what kind of scale factor could we use to turn 230.4 into a 4 by 4? So into 4. So scale factor, why don't we do big to small, and then we can flip it upside down if we have to. And I can show you how to do that. So 230.4 all over 4. So if we were maximizing the base of it, the biggest scale factor we could use smaller ones. We can make it 3 by 3. This is the biggest one we could use. Would be 230.4 divided by 4 is the model is 57.6 times bigger. Sorry, real life is 57.6 times bigger than the model, according to that. Now we have to check. This might not be the right scale factor to use because we need to make sure it's going to fit inside our ceiling as well. So this is an entirely different restriction. So we have a ceiling of 3.5 meters. So we need to check the height. The biggest scale factor we could use would be the height of this thing, which is 146.6. And it must fit inside our 3.5 meter ceiling. So 146.6 inside 3.5 meters is 41.889. We'll round to 2 decimal places. 41.89 times bigger. So which one's actually more restrictive? That's actually interesting. I thought it would have been this one. Did I type it in right? Yeah, just surprising, I guess. It's actually this one is the more restrictive one. No, sorry, I did that. I am thinking backwards. So 1 meter, this is actually a bigger shrink. In this one it says 1 meter in your diagram is 57.6 in real life. This one says 1 meter in your diagram is equal to 41.89 in real life. So this is actually the bigger model because it's closer to reality. So this is actually the smaller one. This is the more restrictive one. So that's our K value. Because there's a bigger difference between real life and the image. There's a bigger shrink. We're actually dividing everything by 57.6. So yeah, I actually got that backwards. So we're going to restrict it this way, so it's going to fit exactly into a 4x4, and then the height will just follow along. It's going to be a little bit away from the ceiling if we want to be perfectly dimensional. What scale factor? So that's our answer for that one. 1 to 57.6. How much glass will the artist need to build this sculpture? Interesting. I could ask you a question like this. I think you guys should be able to do, this is a surface area question. So we need to do a couple things. We need to find out all of our dimensions for surface area. So we're going to need our length and we're going to need our slant height. We actually don't need the real height of the pyramid. That never comes up in surface area. Why don't we actually write what the surface area formula is again? It's going to be the area of this triangle down here, which is going to be length times S divided by 2 for a triangle. And there's going to be 4 of them because it's a perfect square. And to that we have to add, oh wait, the bottom, but do we have a bottom? No, I think we can assume there's not going to be a bottom in this image. Oh, that's hard. I don't know whether to think there's going to be a bottom or not. I'll let you guys decide. If you think there's going to be a bottom made of glass as well, and actually maybe there is going to be, because if you're building a structure, it wouldn't be very stable without a bottom. You know what? I think there is going to be. Let's pretend there is. So on the bottom, it's going to be length times length to make the area of the bottom. So length squared. Okay, let's find these measurements. So our new length is equal to 230.4 divided by 57.6. So it's that much smaller. This should be exactly 4 meters, or round about 4 meters, because that's where we got our number from. I get exactly 4 meters. So our new length is 4 meters. Our new slant height is 186.4 divided by 57.6, the same scale factor. I get 3.2, we're on to 2 decimal places, 3.24. Units, this is meters. Meters. Good, now we just got to plug it all in the formula. In case you didn't know, these actually cross cancel, so this actually just becomes 2ls. 4 divided by 2 is 2. So equals 2ls plus L squared, which is equal to 2 times 4 times 3.24 plus 4 squared. And you can put all that in your calculator at once, as long as you do it properly. And I get 41.92. Units, meters, squared, single, squared, or cubed. Surface area is squared. So therefore, the artist needs 41.92 meters squared of glass. Good. Couple things to tidy this up. This is a big question. After, you'd want to look and make sure you tidy this up. This right here, I might write this in an actual sentence. So therefore, the scale factor is and we ignored units here. You can ignore units as long as you call it units. This could have been kilometers or something. It happened to be meters, so it ended up working out just fine for us. Is 1 meter to 57.6 meters. And I think context can kind of tell you which one's which. Or you could say model to real life. Model to real. Something like that is good. You needed to check this. I think this is the part you would probably forget. You probably would have found this one by using the base. But you have to also check the height. Because say you have really low ceilings, then you wouldn't have been able to build it this big. So you needed to check this. This would have been like a 3-mark question. 1 for doing this, 1 for doing this, and 1 for interpreting the answer. So make sure you don't get only 2 out of 3. This part I think is fairly straightforward. You got to find your new dimensions and then calculate the surface area. That would probably be another 3. 1 for finding the right new dimensions, 1 for subbing in and solving. This is all just kind of 1 mark now. In grade 10 we would do this as many more marks, but you should be able to do this by now. And then state your answer. Okay, that's it for that lesson, and that's it for this unit. Oh, there's more. Oh, I didn't have more of my things. I think I'm going to leave this one for you guys. Try this one on your own, and then you can check with me. I think I have a fairly short lesson with the 20-1s. Try this one on your own, and then check with me, and I can show you the answers after. Summary. Dimensions are related by a scale factor in similar objects. Area and surface area are related by the scale factor squared. Volume is the scale factor cubed. We were using K instead of that. Enlargements, K is greater than 1. Reductions, K is less than 1. So usually we do the new thing, new versus old. And so if the number is bigger than 1, then it's actually an enlargement, and if the number is less than 1, then it's actually a shrink. We didn't do that in this one. This one we did old versus new. So it ended up being 57 to 0.6, but then we turned it into this. If you turn it into the ratio after, that's just fine. Really, it should be 1 over 57.6 if you're doing it the other way. If you flip this upside down, oh yeah, that was the other thing I was going to say. If you did it the wrong way around, all you have to do is flip the numbers. So if this time this was old versus new, and it was 57.6. So solving it the other way, new versus old, is just 1 over 57.6. And fractions are better than decimals. I actually prefer it like that than to see it as 0.0 something. Yeah. Okay, that's it for this unit. You've got both questions and you've got the chapter review because you have the test on Wednesday. Good luck.